Okay, what we're going to do now is some practice graphing polar functions. So I created a polar coordinate plane system. It's awful, but it's all I got. So I worked really hard on this. And yes, it's in a Ziploc bag so that we can use expo markers to graph some of these functions. But that might be better without that light on. Let me go turn another one off too. So I'm going to walk you through some of the types of functions that we need to be able to graph, the ones that we talked about in the previous video. So the first thing we're going to do is identify the types of functions. Oops, still hate it. And then we're going to go through the steps of graphing them. So again, if this is confusing, chances are you need to go back and go over how to graph polar coordinates. So I'll do my best to kind of go through that slowly now, or just stop if you need to and go back and watch it. So we're going to start out kind of simple. We're graphing a polar function r equals 5. And so we talked about in the last video what this is going to produce. So it's a circle centered at the origin, right? So it's centered, circle, centered at the origin. What we're not going to do in this video is convert polar equations into their Cartesian counterparts. You can go back to the old videos, or if we're still having trouble with that, let me know. So this is a circle centered at the origin with a radius of 5. Okay, so what I'm going to do is construct a t-table. So we've got r and theta. So it's really strange at first to kind of wrap your head around the fact that these coordinates are listed as r comma theta, but what we're actually doing is plugging in theta values to get r's out. So it's a little counterintuitive from what we're used to doing. So I'm just going to go ahead and pick angles, just the quadrantal angles. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. And generally these are the ones we're going to pick. Sometimes I'll change them and I'll let you know why I'm doing that. So if I plug in these angles to the equation for theta, I want to know what the output value is. So if I look back at this equation, well, there's no theta to plug it in. So all we're doing is saying r is going to be 5 no matter what the value of theta is. So even if theta was an angle in between 0 and pi over 2, so we know quite a few of them that are in there, or any of these other ones, we would be able to really understand that the output value is always 5. So now let's talk about what that means on this graph. So at 0 radians, the radius is 5. So we start here, and we go 1, 2, 3, 4, 5, and we put a point. And then same thing for pi over 2, it was up at 5. Pi, 3 pi over 2. So in this instance, it may be a little bit difficult, and then back to 2 pi, to see that it is in fact making a circle. So I want you to understand that these are just the points that I picked. We could pick plenty of other ones. So if we're not familiar with the shape of a graph, based on the points that we picked, we can always go back in and pick some more. So what if I picked pi over 4? Again, it doesn't matter what angle I'm picking for this particular function. So I'm picking all my 45 reference angles right now. The output value is always going to be 5 because r is equal to 5 no matter what. So now what we see is a series of points that are lining up around the circumference of this circle with a radius of 5. So I'm just going to connect the dots. And we can see what the graph of number 1 here is, r equals 5. It's just this circle with a radius of 5. Pretty easy, right? Okay. So now let's see what happens. And so in the notes I told you about other types of equations that still produce circles but that are not centered at the origin. So I'm going to use still r equals 5 cosine this time of theta. So now we're taking that value of r and we're multiplying it by the cosine of whatever angle is. So I'm just going to go back up and use these. So now we're just going to see what happens if I go back to this table, and I'm doing this to save space. 0, pi over 2, pi, 3 pi over 2, and 2 pi. So now I have a spot to plug theta in. So what is the cosine of 0? 0 radians. it's 1. 1 times 5 is 5. So we're not seeing a change in the output values. But now when I substitute pi over 2, the cosine of pi over 2 is 0, right? The x-coordinate of 90 degrees is 0. 0 times 5, 0. Plug in pi. If I substitute pi, what's the x-coordinate of pi radians? Negative 1 times 5 is negative 5. I'm going to keep going in that fashion. And this time, what I'm looking at are some different output values when I compare them. So these are the outputs for number 2, right? This equation right here. So if we go back to our circle, we're going to have to change some stuff. So let me see that. See how fancy that is? All right. So here are our output values. So I'm just going to go through the steps of graphing those. So 0 radians, we're still at 5. Pi over 2, we're at 0. So here's my angle, but I'm not going up. It's 0, radius of 0. All right. Pi, the radius is negative 5, so remember we talked about we go backwards. So even though the angle is pi, we're going back over here. So this is the point, negative 5 comma pi. Then we go 3 pi over 2, it's back to 0. 2 pi, back to 5. So what you can see is essentially we're bouncing back between these 2 points. Now, Ms. Schaefer just told us that should create a circle, so why aren't we seeing a circle? So the same reason we talked about over here, it wasn't as necessary to pick different angles over here to see the shape, but it is going to be to see the shape of this circle. So what if we just pick some other angle values? So what if I tried to substitute in pi over 4? So if I plug pi over 4 back into this equation, 5 cosine of pi over 4, so the cosine of pi over 4 is square root of 2 over 2. I'm multiplying then that by 5, which really gives me an output value of approximately 3.5. So I'm just rounding it there. So 3.5. So now I'm going to graph this coordinate, right? I'm going to graph this coordinate. Pi over 4 is right here, right? So along this line, I'm going to go out about 3.5. I rounded 3.5. Okay, and I could pick some other ones, so I did 3 pi over 4. 3 pi over 4, it ends up being negative 3.5. So think about why that's true. So about negative 3.5. And I could pick some other ones, right? What if I picked, instead of 3 pi over 4, 5 pi over 4? 5 pi over 4, right? I could still plug in all these different values. What's going to end up happening, and you can do this on your graphing calculator or any type of calculator, is it's going to produce a circle that has this time not a radius of 5, but a diameter of 5. So if we measure the distance from here to here, this is the diameter. So these 2 points are on the circumference of our circle. This time the point at the origin is on the circumference. So this is a radius then of 2.5 units. So then I would need to go from that center of the circle, 2.5 up, 2.5 down, and what I'm going to create, and this is not at all scientific, so we're about, I don't know, this is awful. There we go. There we go. So I meant to say that we could be checking these on our calculators as we go, so I'm going to just go back to the beginning. So r equals 5. If I want to graph this, okay, that's right, I put this, there we go. So the boundaries are too big, of course, because, see, we're just going from negative 5 to positive 5. So if we go negative 10 to positive 10. Oh, I didn't do the y-axis. That was dumb. But I think you guys get the point. So let me do zoom. I'm just going to fit it. So again, why is it looking like an oval? It's because this is not a square that we're trying to graph it on. We're graphing it on a rectangle. So that's why I like to use the square window. So again, I went zoom, square. Why didn't I do that from the beginning? No one knows. All right, so that was r equals 5. So what are we going to expect to see when we change this now? R equals 5 cosine of theta. All right, there we go. So it's very similar to what we've got right here. And if we were feeling like it, we could always go to our table and get some output values. If we were a little bit confused, when you're graphing these by hand at first, you could be a little confused. I understand that. So I'm just going to change the to ask. And we can see some of the different values. So if I count by pi over 2, just like I did in this table, we're not really seeing anything other than 5, 0, and -5, which is just bouncing us back between those 2 points. So if I want that to be different, I can always change this. Instead of counting, did you see me type pi over 2? We can type pi over 6, sure. And then look at the table. And then see we're getting different values. So we're getting different values. It's helping out a little bit. So you'll be able to graph those. Okay. Let's do something other than a circle. Let's do, well, you guys tell me what this is going to be. R is 3 plus 3 cosine of theta. So look back over at your notes. What's that graph going to produce? Come inside. So that's where A and K are the same. So if they're the same, they're in harmony, just like a heart, which would be a cardioid. So this is a cardioid. So if I want to plot this cardioid, I always start with my quadrantals. So here are my thetas. I'm going to plug them and chug them and see what my outputs are. So I'm just plugging them in for theta, and then I'm doing the math. So the cosine of 0 radians is 1 times 3 plus 3 is 6. Pi over 2, the cosine of pi over 2 is 0 times 3 plus 3 is 3. The cosine of pi radians, -1 times 3 plus 3, well, that equals 0. We're going to keep going in that fashion. So if I were to graph these, 6, 0. 3 pi over 2. So I go to pi over 2 and I count up 3. 0 pi. I go to pi and I come nowhere. I stay where I am, so I'm right at 0. 3 pi over 2, I come down 3 towards 3 pi over 2. And then back to 2 pi, I come to 6. So looking at these 4 coordinates, that doesn't look like a heart to me. Does it look like a heart to you? So the answer to that is no. Why isn't it looking like a heart? Because we need to get some other coordinates on there. So what are some additional coordinates that would help guide me to figure out that this is in fact the shape of a heart, or it's a cardioid? So again, that's where you can hopefully use your brains. Otherwise, you can use your graphing calculator, whatever's closest. I'm just going to show you. I'm going to pick some different values. So let's try, I like to go right smack dab in the middle. So I'm taking pi over 4, right? That's in between 0 and pi over 2. If I substitute that in, so I'm just going to show you what I'm talking about. These are going to be irrational values for pi over 4 because it's going to have a square root of 2 over 2 in there, right? So when we type this in, 3 plus 3 cosine of pi over 4, in case you forgot what that is. And you can see it's going to give us an output value. That is, okay, that's irrational. So it's about 5.1. So 5.4, or I'm sorry, pi over 4 is about 5.1. So now we can see what's happening here. We know what to do in this little quadrant. And if you weren't quite sure, you can plug in some other values to see what's going on. So now let's see if we can pick something in the next quadrant. So I'm going to go in between pi over 2 and pi, and pick 3 pi over 4. Same idea. I'm looking for the decimal value here. That's why I'm allowing myself to use this calculator. 3 pi over 4. So that one's a lot smaller. So about 0.9. So 3 pi over 4, halfway through second quadrant, right? And we're about 0.9. So right about there. Okay? Now if you think about what's going to happen in quadrant 3, if I pick the 45-degree reference angle in quadrant 3, it's going to give me the exact same output because of the symmetry. And we've got here to here, and then same idea over here. So the cosine of the 45-degree reference angle in quadrant 4 is going to give me the same output as up here. So They're both positive, just like over here they were both negative, the cosine values. That's why these are smaller than these, because we're adding negative values. So 7 pi over 4 was about 5.1. So right about here. So now you want to make sure that you connect these points in the order that they come in on the unit circle. So this one to this one to this one, right? Because this was 0, pi over 4, pi over 2. So they have to go in order. The next one was 3 pi over 4. This one, remember how we got this point right at the origin? That was where pi equals 0, or the input of pi, or output of pi. Okay, and then the same thing, we want to just follow the order of the points. And look what we get. A cute little heart symmetric on the x-axis because it was a cosine. If this was a sine, it would be symmetric on the y-axis, so it would look like that, kind of. Okay. Let's see which one I had next for us. Okay, let's try this one. We've got r equals 2 plus 3 cosine of theta. So this is not a cardioid this time because a and k are not the same. This time a is less than k. Less than means this is going to be a loop. Alright, so we're looking for a loop here. I always start this the same way. 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then I just add extra points as I go if I need them. So I'm plugging in 0, and this time, see what we get. We plug in 0, cosine of 0 times 3 plus 2. So 5, I'm going to keep going, pi over 2. This is -1 now, 2, and 5. So I just plugged in these points here, pick the nice easy ones, they have pretty outputs so that it's easy to figure out what my r's are going to be. So now, if we come back to our graph, get this one going, just going to plot these points. So we still have 0 radians over here at 5. Pi over 2 is at 2. Pi, instead of being at 0, pi is at -1. So we don't come out to 1, we go in the opposite direction. -1. 3 pi over 2 here. And then, of course, 2 pi is going to be back to where we started. So again, this should look like a loop. And it doesn't yet. So what are we going to do? We're going to plug in some points. Now, the loop can get a little bit confusing because you're crossing, so I like to go ahead and start numbering my coordinates. So like this one was the first one. This one is going to end up being the third one because we're going to pick one in the middle, right? So let's pick pi over 4. So if I picked pi over 4, and you can pick any number you want in the first quadrant, I'm just trying to get a point. You can pick more than one if you want to. So this time we have 2 plus 3 cosine pi over 4 radians. I have to sneeze. So this 45 pi over 4, we're coming out to 1, 2, 3, 4, and a little bit. This is my second point. So I'm just showing my brain the order to go in. Over here, not as confusing until we get to this middle part. So we can add another point there if we wanted to. We would just change that to number 3 and then this to number 4, whatever. So now let's pick an angle in quadrant 2. So we'll pick 3 pi over 4 again. So 2 plus 3 cosine 3 pi over 4. So when we plug in 3 pi over 4, you can see what happens. Now the radius is negative. Again, so just like it was here. So we're coming backwards. So we're going backwards about 0.1. I'm kind of exaggerating that a little bit just because this marker has such a fat tip here. So this is 0.4, then we go to pi. So now I'm going to pick one in this quadrant. So what's the 45-degree reference angle in quadrant 3? So 2 plus 3 cosine of 5 pi over 4, right? So look what happens. I wonder why. So if we go 5 pi over 4, we're right here. Remember, those two cosine values are going to be symmetric, so they're giving us the same output value. Same thing if I went to 7 pi over 4, it's going to act just like this point right here. So here was 1, 2, 3, 4, 5, 6. You can see already we're kind of getting a little confused. So 6, we come down here to 7. I just need my 8th point, which is going to match this one, which was about 4.12, 1, 2, 3, 4.12. Here's the 8th point, and then we end up here. So I'm just going to connect the dots. This is difficult. 3. So now from 3 to 4. 3 to 4 to 5 to 6 to 6 to 7. And then I just want to mimic the shape that I had up here. So this is the loop that we're talking about. And the loop is happening because A is less than K. It's going to happen anytime that A is less than K. All right. So far, so good. Let's try another one. So now we covered when A equals K, when A is less than K. What about when A is greater than K? So I'm still going to stick to these 2's and 3's here. And I'm still also sticking with cosine. Again, if it was sine, the only difference would be its orientation and symmetry. All right, guess what values I'm going to start with? 0, pi over 2, pi, 3 pi over 2, and 2 pi. So I am going to start plugging these in, substituting them here, and because A is greater than K, what shape should we expect to see? A bean. A little tiny bean. Alright, so plug these in. Substitute, multiply, add. Substitute, multiply, add. Blah, blah, blah. So I'm going to keep doing that. 5 pi over 2 is just 3. Yeah. Okay, this is 1, this is 2, and this is back to 5. Alright, so let's see if we can get this nice little bean shape. Here's our first point, pi over 2. This time pi is at 1, so it's not negative 1, so we're actually going towards pi. And then 3 pi over 2. And then we're back. Oh. Wait, what did I do wrong? This is supposed to be 3. Yeah, this is supposed to be 3. I can't add. There we go. Alright, so does it look like a bean? It sure doesn't. So what are we going to do? We're going to pick some extra points. So handy dandy calculator here. So the equation that we're working with, 3 plus 2 cosine. So I'm going to start pi over 4. So pi over 4, oops, yeah, that's fine. Pi over 4, we're 1, 2, 3, 4, and a little bit extra, right? So here's 0.1, here's 0.2, here's 0.3. Now let's go into this quadrant before we get to our pi point. So 3 plus 2 cosine, 3 pi over 4. So 3 pi over 4 halfway through quadrant 2 is approximately 1.6. Okay? And then, because I understand symmetry of the cosine function, the 45-degree reference angle in this quadrant, quadrant 3, is going to behave just like that. So 5 pi over 4 is about 1.6 as well. So this is 0.4, here's 0.5, here's 0.6, here's 0.7. Now let's come into quadrant 4. So 7 pi over 4 is going to act just like this one. They have the same cosine value, so it's going to be treated the exact same way in the equation. So that means 7 pi over 4 is 1, 2, 3, 4, and a little bit. That's 0.8, and then we end in the same spot. So now you can see this time as we start to connect them in the order that we made them. 1 to 2, to 3 to 4. Oh, I see what I did. To 4, to 5, to 6, to 7, to 8, to 9. Sorry, I messed that up here because I got confused. I actually drew it to the number 4 instead of the point because that's who I am as a person. Alright, so it's a little bean. He just has a little dent in him. This is an awful graph, but if we were to graph it on our graphing calculator, we know it would be a lot prettier. Alright, I've got a couple more. Let's see. This one. So we covered all the limaisons, so now let's do something different. What's that? What's that going to be? That one's weird, right? So hopefully you recognize this one is a spiral. So why is it going to produce a spiral? Let's look. So if I start at 0, go to pi over 2, pi, 3 pi over 2, and 2 pi. So now what I'm doing is just substituting in the angles, doubling them, and that's what the radius ends up being. So what I'm going to do here in this column is give the decimal equivalents of these irrational numbers. So if I plug in 0, obviously the radius is just 0. If I plug in pi over 2, 2 times pi over 2 is pi, so the radius is 3.14 units, right? A radius is a unit, not an angle, so that's why I'm writing it this way. If I plug in pi, the radius is 2 pi, or 6. I plug in 3 pi over 2 times 2, that ends up being 3 pi, 9.42-ish. Plug in 2 pi times 2, it's 4 pi, the radius is approximately 12.57. So we're going to have to round all of these for obvious reasons. So when we took notes on the spiral, we said the smaller the value of k, the tighter the spiral is. So I only made the radius of my polar function, or my polar coordinate plane, go out to 6, so we're not even going to be able to graph most of these points. But I just want to talk about why it's called a spiral. So 0, 0, pi over 2 is 3.14, pi is 6.28, so we're already off the graph, but you can see what's happening. We're going boop, 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 and then, so 3 pi over 2 would be 9, so that would be down here somewhere, and then 2 pi would be 12, that would be way over here somewhere, so you can see the points are getting further and further away from the pole. Further and further away from the pole. Now, I just picked the quadrantal angles, so what would happen if I picked the angles in the middle? What you're going to see, and I'm just going to skip this because I can't really give you a good graph here anyways, is what's happening. They're just going to keep doing this forever and ever and ever and ever. So it's called a spiral because it's spiraling away from the pole. So the bigger the value of k, then the further away this first point is, which means the further away the second point and the third point, etc., etc. So that's why we call them a spiral. They're pretty easy, kind of fun to draw if you're bored. All right. So the next thing I want to talk to you guys about is roses. No, let's not. Let's do this one. So remember, when we have the square root sign like this, it has a special name, a lemniscate, because it's a figure 8. Alright, so if we have r and theta, we have 0 and pi over 2 and pi and 3 pi over 2 and 2 pi. So when we go to plug these values in, plug in 0. 2 times 0. That's 0 radians. The cosine of 0 radians is 1. 1 times 16. 16, the square root of 16 has a radius of 4. Easy. Pi over 2 times 2 is pi. The x-coordinate of pi is -1 times 16. This means we're trying to take the square root of a negative number. So, for our purposes, there are no imaginary values on the polar coordinate system. So this would be an undefined radius, which doesn't have a radius. If we plug in pi, cosine of 2 pi is the same as 0, so we're going to get 4. 3 pi over 2 has the same x-coordinate as pi over 2. Again, it's undefined. Sorry, I got distracted. And then we're back to a 4 again. We're ending in the same spot. So, is this going to be enough information to get us a figure 8? Well, let's see if we can figure that out. So we've got these coordinates. So at 0, we're over at 4. At pi over 2, we can't graph anything, right? There's nothing, literally nothing to graph. At pi, we're over at 4. 3 pi over 2, we can't. And then 2 pi, we're back over here. So the answer to is this enough to create a graph? The answer to that is no. So what are we going to do when this happens? We always pick some other coordinates. So we'll start with pi over 4. So if we plugged in pi over 4, right, if we plug in pi over 4 here, it's 2 times pi over 4. that's pi over 2. What's the x-coordinate of pi over 2? It's 0. Times 16 is 0. What's the square root of 0? It's 0. So pi over 4 is here. So was that necessarily helpful? Let's try 3 pi over 4. 3 pi over 4 in quadrant 2, if I substitute that in, I get 6 pi over 4, which is 3 pi over 2. The x-coordinate of 3 pi over 2 is 0, times 16 is 0, square root of 0 is again 0. So while it added a coordinate onto our coordinate plane, it's not enough to get us this figure 8 that we're looking for. So this is an instance where my trick of picking 45-degree reference angles ain't gonna work. So what if we tried some other ones? Let's start with 30-degree reference angles. So what if I substitute in pi over 6? 2 times pi over 6, 2 pi over 6 is pi over 3. What is the cosine of pi over 3? So what is the x-coordinate of 60 degrees? The x-coordinate of 60 degrees is 1/2, right? 1/2 times 16 is 8. So at pi over 6, the radius is the square root of 8, or 2 square roots of 2, or approximately 2.8. Close enough. So if we started with pi over 6, right? Yeah, that's what we did. We started with pi over 6, that's here. We're about 2.8, 2.8. Now, if we think about it, the fourth quadrant angle, 30-degree angle in the fourth quadrant, is going to have the same output. So now I need to come over here and find my 30-degree reference angle. So instead of pi over 6, I'm going to pick 5 pi over 6. I'm doubling that, so that would be 10 pi over 6, 10 pi over 6, or 5 pi over 3, 60-degree reference angle. So now we've got a cosine that's, wait, what did I just say? I need to erase this stuff. Sorry, my brain's not working. There's too much going on. So if we were to pick, let's pick theta is, okay, we did quadrant 1, now we need quadrant 2. So what about 5 pi, no, why can't I make my brain work? We picked pi over 6, yeah, 5 pi over 6. Okay, so I'm substituting in 5 pi over 6, which is 2 times 5 pi over 6, 10 pi over 6. So really, it's the square root of 16 times the cosine of 5 pi over 3. Right? No. Why can't I do math, you guys? Is it? Anyways. Alright, so what is the cosine? It is. What's the cosine of 5 pi over 3? So it's a 60-degree reference angle. So now we've got, because this is in quadrant 4, it's 1/2. So again, we're looking at that 2 root 2, or about 2.8. So if we plug in 5 pi over 6, which is in this quadrant, right? 5 pi over 6, it is 2.8. 2.8. 2.8. And then same thing, it's going to be 2.8 down here for the same reasons. So now we're looking at a little bit of this figure 8. There we go. Sorry that took so long. My brain is dying. Alright, so good lesson here is if you pick some coordinates or some extra angles here and it's still not enough to produce the graph, then you gotta keep picking some more. And use your calculator so that you don't have brain farts like me. Alright, so the next thing I want to talk about is the most complicated. So now we've got these roses. And they're complicated just because they have a few extra rules involved in them. So they are strange. And you're going to have to memorize a couple things here. I apologize. So the first case I want to talk about is cosine roses. So cosine roses are easier than sine roses. They have some of the same rules that overlap, but sine roses have their own little subset of rules. So I'm going to start with 3 cosine of 4 theta. And we talked about what the two different values mean. So this is our k value, k equals 3. This means that the petals are 3 units long. We also want to know how many petals there are. So we look at the value of b. b is 4, that's an even, which means there's going to be 8 petals. Alright, so I'm going to make this as easy as I can for you. We actually aren't even going to use a t-table for this. I just want you to think about this. We have 8 petals that need to fit within that 0 to 2 pi. Right? So if we were to construct a t-table from 0 to 2 pi, we need 8 petals. Now these are symmetric petals. So what does that mean? We're dividing the 2 pi into 8 petals. So how big is each petal? Each petal is pi over 4 apart. So there are 8 petals that are pi over 4 radians apart from each other, and each of them are 3 units long. So let me show you how easy this can be. So, our first petal on cosine is going to start at 0. So it's 1, 2, 3 units long. So there is going to be the tip of the first petal. So I need 8 more of these. So every pi over 4, I'm going to put a petal. So pi over 4 is one of the petals. And so pi over 4, here's, so 0 plus pi over 4 plus pi over 4, plus another pi over 4, another pi over 4, another pi over 4. So every pi over 4, I'm putting a dot that is 3 units away from the pole. So 3 units because each petal is 3 units long, and 8 dots because these are going to represent the 8 petals. So all of the petals connect at the pole. So it's as easy as just drawing pretty little petals that connect at the pole. So this is the graph of this function, if you understand how roses work. So I can show you on a t-table why this is true. The door's open, that wasn't my butt. Alright, so 0, I know that I'm going to get a petal every pi over 4, so that, I already know that I'm going to choose to set my t-table up this way. Pi over 2, 3 pi over 4 to pi. So I'm just going to work through these up until pi so that you can see what's happening. So if I plug 0 in, cosine of 0 times 3. So there is our first coordinate. And we can see that we got it right. There she is. Right? If I substitute in pi over 4 times 4, that's pi. What is the cosine of pi? Negative 1 times 3. So this is negative 3. So here's maybe the weirdest part, or the first weird part. At pi over 4, this isn't actually the coordinate that represents what we just found. Pi over 4, it's right here. This is that coordinate. Isn't that weird? Okay? If we plug in pi over 2, 4 times pi over 2, 4 pi over 2 is 2 pi, so we're back to 3. Right? So 2 pi, we're back to 3. So if we look at pi over 2, you can see here's our coordinate. And we can just keep going. So I think you guys are going to get it. But it would just require a lot more of the in-between points that we were talking about to really get the shape of this graph. So if you understand how roses work, it's just going to make your life a lot easier. Alright, so now let me show you a rose that has an odd b value. So r equals, I'm just going to swap them, 4 cosine of 3 theta. So now our petals are 4 units long, which that just means I'm going out to 4 instead of to 3 like I did here. And B is 3. Let me just label that. B is 3. 3 is an odd number in case you didn't know, meaning this graph only has 3 petals. So when it's odd, it just has that amount of petals. When it's even, you double the amount of petals. You double 4. When it's odd, you just keep it the same. I know that's weird. It's just the way it is. It has to do with the symmetry. All right, so now if we think about this, we need 3 petals over the whole loop around the circle. So there's a petal every 2 pi over 3. So they're 2 pi over 3 apart. So let's look at this graph. We're going to do it the easy way, and then I can show you the hard way. So it's a cosine, so the first petal is always at 0. Always, always, always. So 0 radians, and then we come out. This each petal is 4 units. 1, 2, 3, 4 units. Okay? So the next one is 2 pi over 3 away from this one. So because we're starting at 0, the next one's just going to be at 2 pi over 3. So it's 0 plus 2 pi over 3. Well, that just equals 2 pi over 3. So that's 2/3 of the way through the circle. Okay, so it's here. What was our radius for? 1, 2, 3, 4. Okay, so now 2 pi over 3, my next petal should be another 2 pi over 3 away, which is 4 pi over 3. So where is 4 pi over 3? Yeah, that's right here. In a perfect world, these would be numbered. Like the angles would be here, but I didn't have time for that. Alright, so now we can see where the ends of our petals are. I drew a point on the pole because all of these need to connect at the pole. So there is something to be said about the width of the petals, but for now, there we go. I have not even been checking my answers as we go. You guys are just trusting that I'm right. I know you are. Alright, so this is the one we're doing right here. 4 cosine 3 theta. Let's do... So it looks pretty darn similar, doesn't it? Pretty darn similar. So the shortcut's nice and easy. So next, final thing, last 2 graphs are sine roses. So sine roses are a little weird. So I'm going to start with 3 sine of 4 theta, which is really similar to the 3 cosine of 4 theta. So again, K is 3, so each petal is 3 units long. B is equal to 4, and B equal to 4 still means we have 2 pi, a distance of 2 pi, we're splitting it into, oh, sorry, I don't know why I did this. So, I skipped a whole step. So if B is equal to 4, that's even, meaning there are 8 petals. So I'm not dividing by 4, I'm dividing by the number of petals. So each petal is pi over 4 radians apart. The difference with this is we're starting at a different spot. We don't start at 0. This is the weirdest part, is the starting petal. And it's a rule, and it's always pi over 2, which is the first time the sine function is equal to 1, just like the first time the cosine function is equal to 1 is at 0. Here, it's not. It's pi over 2 because we're talking about a sine function. But we don't just start it always pi over 2. It always has to do with what the value of b is. So it's pi over 2 times 1 over b. So if b is 4, this is pi over 2 times 1/4, or pi over 8. So while the petals occur every pi over 4, we're starting at pi over 8, which I know is really weird. So let me show y'all what I mean by that. So pi over 4 is just 1/2 of, pi over 8 is 1/2 of pi over 4. So if this is pi over 4, pi over 8 is smack dab in the middle. So every half of 45 degrees is going to be the 22.5 or the pi over 8. So the first petal has to start at pi over 8, so we're not putting it here at 0 because this is a sine rose. So pi over 8 is the starting point. So I'm going to put a point at 3, 1, 2, 3, pi over 8. So there's my first petal. The next petal happens a distance of pi over 4 from this. Not at pi over 4, that would be if we started at 0. It's pi over 4 from that angle. So this angle is pi over 8. If I'm adding 45 degrees, my next petal is going to be right here. Okay, so if that was confusing, what I just did, and this may be helpful to you as you think about graphing these. So if we start at pi over 8, that's petal 1. I'm adding pi over 4. So if I'm adding something to a denominator of 8, I'm just going to go ahead and rewrite this. So if I want this to be an 8, then this should be 2 pi over 8, right? So I'm adding 2 pi over 8. So where's my next petal? Petal 2 is at 3 pi over 8. And if that was, not making sense to you, you could always convert it to degrees if that was helpful. So then I take this 3 pi over 8 and I add another 2 pi over 8. So my third petal is at 5 pi over 8. And then my next petal, I'm adding another, so it's 7 pi over 8. So all of these so far are still in the top half, like they're in, but we haven't made it to pi yet. And what's happening is, you guys can't even see what I'm doing. So I'm just going to put the halfway point, and then halfway of the halfway point is going to be the next petal. 3, 3, and I'm just going to keep doing that. Halfway of the halfway point. This is not perfect by any means. I used to talking this much. 2 videos in one day. Who do I think I am? Alright, so how many, I'm going to count my points to make sure we have 8 petals. 1, 2, 3, 4, 5, 6, 7, 8. Bingo! And they are all, because I did my increments here, they're all perfectly aligned. So I'm going to get rid of all of these lines because they're not part of my graph, and it's just going to make it look even messier than it needs to be. So the final thing I do is draw my point at the pole, and now I'm just going to make a bunch of little petals. And we're going to check our answer to make sure that we're good. So here is our function, 3 sine of 4 theta, and graph. So obviously you can see the order that this graph's in was different because of the shortcut that I'm using. So you can see we're good. We did it. All right, final graph is R equals, so I'm just going to swap them for sine of 3 theta. So K is 4, so each petal is 4 units long. And B is 3, this is an odd number, which means there are only 3 of those petals that are 4 units long. And how far apart are they? 2 pi over 3. I'm splitting the 2 pi into the 3 specific petals, so they're 2 pi over 3 apart from each other. But because this is a sine function, I have to figure out where we start. We're starting at pi over 2 times 1 over b. So pi over 2 times 1 over 3. So we're starting at pi over 6. We're starting at pi over 6. So we start at pi over 6. Sorry. Just making sure I did everything right. Okay. Making sure I covered everything before I have to end this video in a second. Alright, so let's go ahead and put our starting point on. So we only have 3 petals this time, not too shabby. So we are starting at pi over 6. Pi over 6 is 30 degrees. So 30 degrees, and then our length is 4. 1, 2, 3, 4. So here's our first one. Alright, so let's figure out where the other 2 petals are. So petal 1, pi over 6. Petal 2 is going to be pi over 6 plus 2 pi over 3. So 2 pi over 3 with a denominator of 6 is 4 pi over 6. So the second petal is at 5 pi over 6. Petal 3 is 5 pi over 6 plus another 2 pi over 3, or another 4 pi over 6, which is 9 pi over 6, and that would be 3 pi over 2. So here are the other points where my petals are going to be. So 5 pi over 6 is 30 degrees away, and 1, 2, 3, 4, and 3 pi over 2, 1, 2, 3, 4. So when you graph these, they should be pretty symmetric. They should be for about the same distance apart. And here's my pole. And now I'm just going to graph these, or make little petals out of them. Alright, let's see how we did. 4 sine 3 theta. Boop. I would say that's pretty darn close. So again, ours is not going to be perfect, especially with this bootleg polar graphing coordinate system that I created for you guys using this. I used this. So, anyways, that should be it in terms of graphing these. So, if you can recognize what the shapes are, it'll make your life a lot easier. I wish I could give all of you this graphing paper. Hopefully you have a printer. Hopefully your parents make more money than I do. But if not, you can make your own. It's beautiful. Or use your graphing calculator, or use one of the 2 links that I sent you today in the remind. Okay, bye!